So we'll move into the last subject in this lecture that was mostly about resolution. We started off with scale, map scale mostly, and then we moved on to sampling frequency, resolution, and now we're going to go into something called resampling. This is connected to resolution, specifically our nominal spatial resolution, where we have a raster with cells or pixels, depending on what data we have. So here we have some part of a raster, and we're going to need to do something called resampling because we are going to change something about this raster. The first illustration is we're going to rotate it. Why might we want to rotate this? Well, we're doing a transformation from one coordinate system to another. Our satellite data, for example, or even the aerial photographs, when those images are acquired, they tend not to follow a coordinate system. They're not flying along north-south lines according to our maps, according to the coordinate systems that we want to use. They're doing their own thing, as it were. So we get the data, and then we want to transform them so that they are aligned with our other data, with our coordinate system. We're not changing the size of the pixels, generally. We're just rotating them in this first instance. So we want to put some data into this new pixel here. This is the red grid here is our new coordinate system raster. So we want to get the information to put into this red pixel from the black grid. Well, that's fairly straightforward. We can take the values from there and put those into the red. Up here, well, it's fairly straightforward. I mean, it's probably okay to take that. We've got a little bit going into there, and we've got that's kind of not quite right. It starts to feel a little less satisfactory. And then when we look at a case like this, where we've got this pixel here, well, then we've got 4. We really do want to get data from all 4 of those. So how do we do this? We can't say that any one of those pixels is more that one than any of the other. So which one of them is it that applies there? This is what resampling has to cover. There are several different methods, actually more than I'm showing here. Some of the most important, though, are going to be nearest neighbour, where we look for the nearest value and just transfer it straight over, like a translation straight over to the new pixel location. This preserves the values that were in the original image. We don't create any new data. This is if you're going to resample classed data, so you've interpreted an image, say, and you've got a raster of classed data. So here is wheat and here is rye, my favorite examples. There is no class in between there, not in a meaningful sense. So you can't start interpolating between those. You just have to say this is either wheat or rye. It's not Y or wheat. So that's but we also want to use nearest neighbour sometimes even with continuous data, in remote sensing data, because we don't want to influence the statistics of our image too much. We want the statistical distribution, that the values that are available in that image to be the same as in the original for various purposes of classification and so on. If, however, we think that we can get away with slightly altering the values in the image, we can do something called, I say, a bilinear interpolation, which looks at the pixels in the immediate vicinity and does a linear interpolation between those to create a new value. Bicubic starts to look at the neighbours of the neighbours to see if we can find trends in the rate of change of the signal. And then we could do other things like a weighted average to look for the most common value in an area around it. Similar to running a kernel, as we've done in previous lectures. So let's just illustrate some of these. We're going to do the illustration by looking at resampling to a larger pixel size or larger cell size, just because it's easy to illustrate. But this also applies in this situation. We might want to resample to a larger raster because we want to work with other data as well that has that resolution. We're going to make it compatible with that data. And we also, I should stress right now, we generally speaking only go from high resolution to low resolution, resampling that way. Resampling the other way, from low resolution to high resolution, is generally speaking a no-no. We don't do that because you're introducing information that isn't there, or worse. But let's just look at how these different resampling methods might work when going from the higher resolution data to a slightly lower resolution data. So here we have the general setup that we're looking at, and this is the side view of this. So the position here represents the value across that is shown in these cells. And these are the cells or pixels here, the size of them as well from the side. And in the original data, this is the high resolution data. We see what a value there, and a value there. And then we're going to try and transfer this to our slightly lower resolution image. So this is a cell over here, and this is a cell over here. Which value are we going to put into this cell, and which value are we going to put into this cell? With nearest neighbour, we simply transfer over the value that was nearest the centre, if we're using the centres as our reference point. So no change has been made. We can see that the value of the new pixel has been taken from an existing value, an old value. This one has been left out. It's dropped. It no longer exists in our data set, in the new image. This can happen even when if we use nearest neighbour on a rotation where we still have the same pixel size. This can happen in some circumstances. Some areas we will lose pixels, so we'll get a doubling. So that's a little bit of a problem, especially if we want to maintain our statistical distribution. But it's perhaps something we have to accept, or at least be aware of. So that pixel gone. Bilinear, a bilinear interpolation. We go from the higher resolution where we have these 3 pixels here to our lower resolution with just 2 pixels here. The linear interpolation here, we go from pixel center to pixel center there along this line, and our new pixel center is going to be here. This is the center of the pixel, and so the value is simply traversing this line that goes from that center to that center, and where that crosses, that's the value that we're going to take. That's a linear interpolation. The distance along there gives us the new value, and we do the same thing in the next. So we get these 2 new values. We can see that neither of these values were in the old image, certainly not at this location. So we've created 2 new values that weren't there. And as you can see, this is not going to work for class data, because if these here represent particular classes, where are we now? They can be completely irrelevant values. They might not exist at all, or they might just mean something else entirely, depending on how the data has been classed. So we can't use this bilinear method when doing when we're talking about class data, but useful for continuous data. And it's bi rather than just linear, because here it's just simply linear. It's bilinear because we're also doing this interpolation in the direction going in and out of the screen as well. We can't really see here. Difficult for me to illustrate. The weighted average the illustration ends up looking pretty much exactly the same as the previous. So I won't bother with that. The mode is just, as I stated before, we just take the most frequently occurring value. That's only going to work with class data as well, really. we're not likely to be able to use that on continuous data. So returning back to that point that I mentioned earlier, and I'm going to mention it again because it is quite important, you should almost never resample to a higher resolution. You should basically never do this because you're saying that you now know more about what's happening in each pixel. So to begin with, we have this black pixel here. We gathered information. We'd sampled this. However we've gathered that information, whether this is remote sensing data or another type of data, we said that something here. And we don't say exactly where within this pixel that information is. It exists over the entire pixel. And then we increase the resolution. Well, now we're saying that we know something about this particular corner of that pixel, and we know something about this particular corner of that pixel. But where did that information come from? Unless we have another data source that we say correlates with this, and we can make a reasonable interpretation from that correlation, unless we gather extra data, unless we think, I'm pretty sure that there's some periodic signal in this, perhaps you can make that assumption. Is it valid? That's very difficult to say, and it's going to vary. Then you cannot do this. And a good illustration of why this is a difficult thing to do, if we look at, say, elevation and we want to look at slope. So we have a particular support. We've measured data for elevation using a particular size, a particular footprint on the ground, so-called the support. I'm going to measure this area, and that's the elevation. Obviously, elevation on the ground can vary in a minute scale. I mean, if we really want to, we could use get very close and measure minute changes. But that's not what happens. We step back to by many steps and measure over a larger area. Whether we're standing there with our GNSS with a stick measuring a particular point, the surveyor is standing there looking down at the ground and saying, well, this is fairly representative of this area around me. Or whether we're using a laser to measure the ground, measuring thousands of points with a particular size of the laser as it hits the ground. Might be have some spread, but we're also filtering out a lot of those laser measured points and averaging them out over a particular area. There's still a particular footprint, a particular support for each raster cell pixel that we have, saying that this is the elevation. We've got the elevation at that particular area, and the slope that we can derive is dependent on that size. So here we have our cells, and then the slope as we go from one cell down to another is that slope, because slope is determined as the change in elevation by the distance over which that change occurs. In this case, it's the cell size. So we've gone from there to there over this distance. So that's the slope. If we then resample this to a higher resolution, well, then all of a sudden our slope is much higher, much greater, because that change in our elevation is still the same over here. We've not done anything about that, and then all of a sudden it just goes down like that. We could, in theory, try doing something like bilinear interpolation, and that might improve the situation a little bit, potentially. But as I mentioned, we have this idea of the support, the resolution of the data themselves, over which area is that measure of elevation considered accurate. And if we start doing things like interpolating between two different measurements, we will be interpolating a variation at a different scale. And then we start calculating the slope on that. Well, we're calculating the slope of something different. The resolution of that slope is not the same as the resolution that we're actually using. It may feel like a strange concept, but believe me, this can have effect. It might not always be obvious when you do these calculations, but you will. You do definitely see the problems occurring. You'll get like terracing features in your slope data that just aren't there in the original DEM. So if you're seeing that, it's because you've resampled to a higher resolution when you shouldn't have. So you can resample the data after you've done the analysis. For things like visualization and for compatibility with other data, do all of your analysis in the correct resolution, and then you can potentially afterwards resample to a higher spatial resolution when you're not going to do anything more with that data other than just combine it with other features. So that was resampling.